Okay, Matt Roscoe here at the University of Montana, a continuation of our lecture on the greatest common divisor for Math 326, number 3. So we've already defined divisibility, and we talked a little bit about the divisibility theorems. Here was our definition of divisibility. These were the 7 theorems that are provided in your text. We proved those, I guess, 3 theorems. And then we went on and did a divisibility example problem and proved this statement. And then we defined the GCD, and it's both an integer that is a common divisor to A and B, as well as the greatest among divisors to A and B. So that's the definition. We took a look at some numerical examples, and then we got to this theorem. And that's where we left off. So we should probably go here next. It says that given any integers a and b, not both of which are 0, there exist integers x and y such that the GCD of a and b is equal to ax plus by. So what does this theorem really mean? Well, it means that we can always construct a linear combination of a and b such that when we combine that linear combination or create it, there is an integer, or excuse me, there is a result that results in the GCD. I would like to say that this isn't unique. It just says it exists. So make sure you understand that. So let's look at an example. If A is 24 and B is 16, then the GCD is 8. And so what the theorem would say is that there's some x I can multiply 24 by, some y I can multiply 16 by, and combine to result in a GCD of 8. Or to result in 8. So let's take a look here. So let's say if I look at all the linear combinations of A and B, starting with 1 for x and 1 for y, so 1 times 16, 1 times 24. If I add those together, I get 40. 2 times 16 plus 1 times 24, I get 64, and so on. So you can see that there are lots of numbers are potential linear combinations, but none of them seems to be at this point equal to 8. This is your search box down here. So it appears that what we need to do is move our range of investigation to the left on the number line. So I'm going to type in negative 10 here, and suddenly some 8s start popping up. If I type in negative 10 here as well, then I can see a few more 8s. And so we can see that the 8s lie on a diagonal here along sort of the transition from results where the linear combination is positive to where the results are negative. And in fact, if you look closely, you'll see that 8 is in fact the smallest positive integer that is a linear combination of A and B. 0 being not positive, but so you can see you can also get 0 out, but in terms of the positive linear combinations, it's the smallest positive, the least positive linear combination of A and B, and that'll be instrumental in our proof. So let's go ahead and switch over to the desktop and take a look at a proof of this statement. Okay. Well, let's see here. So what do we want to prove? I guess our hypothesis is just the statement of the theorem that given A and B integers, not both 0, there exists an x and y in the integers such that ax plus by is equal to the GCD of A and B. Okay, so how does the proof work here? Consider the set, let's call it S. This would be AU plus BV such that AU plus BV is strictly greater than 0, and U and V are elements of the integers. So this is a set of, I guess we could think of it as all possible positive linear combinations of A and B. we're going to argue the set is non-empty, and then based on our numeric evidence, we're going to argue that the least element of the set is actually that number, the GCD. So here we go. S is non-empty. Why? Because assuming without loss of generality that A is not equal to 0. So we know that one of these two numbers is not equal to 0, so let's assume it's A. If we assume A is not equal to 0, then the integer absolute value of A has to be in this set, and I'll show you why that's true, because we can say the absolute value of A is going to be A times some number, I'm going to call it T, plus B times 0. So first of all, notice that that it meets the form for being in the set, but what we have to guarantee is that it's positive, and all we know is that A is an element of the integer, so it could be positive or negative, and that it's non-zero. So what we do is we say we sort of set some stipulations on T. We say that where if A is greater than 0, then T is equal to 1, and if A is less than 0, then T would be equal to -1. So all T does is adjust the sign on A. It guarantees that it's positive, but in one of those two cases, this number will always be in the set, regardless of the sign of A. So I think we've shown that it's non-empty. We apply the well-ordering principle and claim that S must have what? A least element. And that least element, we're going to call it D. If it's in S, it's got to be written as some A times some integer plus B times some integer. But in this case, I'm going to just show that that this is, it turns out that we're going to use X and Y for the arbitrary, for the linear combination of A and B. And what are we going to show? We're going to show that that D is actually the GCD of A and B. And here's how we'll show it. By the division algorithm, what we're going to do is we're going to divide A by D. So by the division algorithm, what we get is we get A is equal to some dq plus R, where R is greater than or equal to 0 and less than D. And we're going to solve for R. What we'll get is R is equal to A minus QD, which is A minus Q, well, D is AX plus BY. Doing a little rearranging, we'll find out that that's A times 1 minus QX plus B times negative QY. And that's a 1. And so I can see then that R is a linear combination of A and B, but we know that R is between 0 and D, right? And D is the least element in S. It's the smallest linear combination. And S is only positive linear combination, so that really seems to imply then that R has to be equal to 0. And if R is equal to 0, we can make some nice conclusions. So that's what we're going to argue. We're going to say now if R were positive, then it would be in S and less than D which is a contradiction because D is our least element in S. So what do we conclude? We conclude then that R is equal to 0, right? If R is equal to 0, well then A must be equal to DQ. And if A is equal to DQ, then that means that D divides A. Ooh, that's nice, because what we're trying to show is that D is the greatest common divisor. What we've shown is that it is a divisor, at least. We'd have to show the same thing for B next. But I don't know if you noticed, but we could go through this same argument, just replacing A's with B's, and come to the same exact place. So all I'll say is by a parallel argument, B could be equal as to some DQ prime, which seems to imply then that D divides B, right? So what have we shown? We've shown that that D is a common divisor. Of A and B, right? So what we need to show is that all other divisors are less than or equal to D, right? Let's let C divide A and C divide B, right? So this would be another common divisor. Of A and B. Well, then if it divides A and B, then C will divide any linear combination of A and B, which means that we could say a statement like this: C will divide AX plus BY. That's a linear combination of A and B. And we know that AX plus BY is actually equal to D here, right? So C will divide D. Now, since C divides D, we can say what? Well, what's true about a number when it divides another number? Well, one of the theorems that we have in the divisibility theorems is that if a number divides another number, its absolute value has to be less than or equal to the absolute value of the other number. So it could be equal to D, but its absolute value must be strictly less than the absolute value of D. Well, but since D is strictly greater than 0, because it's in S, and S is strictly greater than 0, its elements are strictly greater than 0, we have, the absolute value of C strictly less than or equal to D, which is just anytime an absolute value is less than some positive number, then we can just say that C must be indeed less than D. And what does that mean? Well, it means that anytime C is an arbitrary common divisor of A and B, it's got to be less than or equal to D, so D must be the greatest common divisor. Is the GCD of A and B, which is what we set out to prove. So hopefully that makes sense. I'll go ahead and escape out of here, minimize this. Okay, so we feel like this makes sense. The GCD of A and B is always equal to some linear combination, or we can always find a linear combination of A and B. Let's go ahead and well, it turns out that there's another theorem that says that if we think about any integers A and B, again, not both of which are 0, then the set T, which is the set of all linear combinations of A and B, in other words, take every X and every Y and construct a linear combination of A and B, is precisely the set of all multiples of of the GCD. And this one we're not going to prove, but I do want to show it to you at least numerically. So let's go back to our numeric example. We have A equal to, well, let's pick something easier. How about 3, no, let's see, 15 and 18. Okay, so their GCD is 3. Here's a whole bunch of linear combinations of 15 and 18. And what you should notice is that every single one of these linear combinations is divisible by 3. One way you can check that, of course, is to use the divisibility rule for 3, adding up the digits. If the digits sum to a multiple of 3, then we have an integer that's divisible by 3. So every single one of these is going to be divisible by 3. Also notice that, if I type in 3 into the, that certainly the GCD is one of the linear combination options. Just to make this completely clear, what I did in the next sheet is I took all of these linear combinations and I divided them by the GCD. So this is what all of the linear combinations divided by the GCD look like. So here you see the 3 divided by 3, which is 1. And what I guess this proves, or at least seems to give strong evidence towards, is that there isn't any decimal division going on here, any remainder. So it seems like things are indeed divisible. So once again, I'm not going to prove this one, but I'll let you read your book and take a look at that statement in your book, and we'll go through and prove one more here. Here's an important theorem. It says that given any integers a and b, not both of which are 0, then if the GCD, then GCD of a and b equal to 1 is true if and only if there exist integers x and y such that the linear combination of a and b using x and y is equal to 1. Now this seems somewhat intuitive. I mean, if we go back and look at this one, if I replace the GCD with 1, but one thing I want to draw your attention to is that this is an if then only if. So in other words, it goes both ways. If I can find a linear combination that's equal to 1, then the GCD has to be 1. If the GCD is 1, then there is a linear combination that's equal to 1. We also have a special phrase that we say when a GCD of 2 numbers is equal to 1, we call them relatively prime. So when 2 numbers are relatively prime, there exists a linear combination equal to 1. Let's go ahead and prove this theorem. All right. So our hypothesis is that, the preamble would be let A and B be integers, not both 0. Then what we know, or what we're setting out to prove, is that if the GCD is 1, that happens if and only if we can find a linear combination ax plus by is equal to 1 for some x and y in the integers. Okay, so how does the proof work here? So we've got 2 directions to go. I'm going to start with the forward direction. Let a and b be integers, not both 0. And let the GCD of a and b be equal to 1. Then by our previously proved theorem, ax plus by is equal to 1 for some x and y in the integers. In other words, the previous theorem basically says this works fine, right? If you know the GCD, then you know there's a linear combination of the GCD. a linear combination equal to the GCD. Now, probably the harder part or the more novel part is the converse here. So for the converse, what are we going to say? Let's see. So for the converse, we assume, right? Suppose that ax plus by is equal to 1 for some x and y that are in the integers. And then what we're going to try to say is we know that a and b, if both of them are not 0, have some GCD, so we're going to let d be the GCD of a and b. So what do we know? Let G be the GCD. We know that it's a common divisor, right, of A and B. So D must divide A and D must divide B. So D must divide any linear combination of A and B, right? So let's let it divide AX plus BY, right? So that's our last theorem in the divisibility theorems. And, well, what is AX plus BY equal to but 1? So D divides 1, and D must be what? Well, anything that divides 1 must be, I mean, there's only a finite number of choices now, must be either 0, -1, or 1 itself, right? But since D is the GCD, D has to be greater than 0, right? Because the GCD is always greater than 0. So we conclude, I guess we should probably, by the definition of GCD, so D must be equal to 1, right? And what have we shown? Thus, the GCD of A and B must be equal to 1, which is it's exactly the converse of the statement, right? Given a linear combination equal to 1, we can conclude the GCD is equal to 1. So that's a really powerful, I guess, converse. So we have shown that if A and B are elements of the integers, both not 0, that the GCD of A and B equal to 1 occurs if and only if AX plus BY is equal to 1 for some X and Y in the integers as desired. That's what we wanted to show, right? Okay, so that's the proof of that statement. I will say there's a couple other theorems that are important in the chapter I'm not going to prove. Here's one of them. It says that the GCD of A and B is equal to D. If that's true, then you can compute the GCD of A divided by D, B divided by D, and it will always be 1. That should somewhat make sense to you, right? I mean, if the common divisor of A and B is completely captured in D, then dividing it out will result in two relatively prime integers. Make sure you understand that A divided by D and B divided by D are always integers, right? Not fractions here. You can look for the proof of that in your text. Here's another interesting theorem. It says that if A divides C and B divides C with the GCD of A and B equal to 1, then the product of A and B will divide C. Okay, so that's an interesting, it seems unusual because, products tend to grow, but if the GCD of A and B is equal to 1, then you can apply the product. There's a really nice proof of that again in your book. For brevity, I'm going to go ahead and let you read that on your own and skip to one that's sort of similar in structure. This is Euclid's lemma. It says that if A divides a product B times C, and the GCD of A and B is 1, so this number and this number is 1, then we can conclude that A must divide C. So we'll go ahead and prove this one, and we'll be using it quite a bit, so it might be a good one to get familiar with. Okay, so here we go. Here's our hypothesis. If A divides BC with the GCD of A and B being equal to 1, then we can conclude that A will divide C alone. Okay, so here's our proof. We're going to start out with the premise, so let the GCD of A and B be equal to 1. Then what can we conclude? Then there's some linear combination, AX plus BY equal to 1. Some X and Y in the integers. So multiply both sides by B. What do we obtain? By C is what I want to say. What do we obtain? We get ACX plus BCY is equal to C. I'm going to call that equation 1. Now, since A divides BC, we have, let's see, so if A divides BC, then I can multiply A by some integer D. So AD must be equal to BC. I'll put that out here, AD equal to BC for some D in the integers, right? Then I'll call that 2. So substituting 2 into 1, what do we get? So what I'm going to do is I am going to substitute in for BC this AD. So we'll have ACX plus ADY is equal to C, which is just A times CX plus DY is equal to C. And that shows what? That A divides C, which is what we set out to prove. Okay, I guess I should put the cap on there. So indeed, that does seem to work. That's Euclid's lemma, and let's do one example. This shouldn't really say theorem. It should say GCD example. Let's try this one as an example. The GCD of 2a plus 1 and 9a plus 4 is equal to 1 for any integer a. That's a very interesting, I guess, example. It seems almost unlikely. Let's just make sure it's true. If I can find my, I think I have a, here it is. So for a equal to 1, 2a plus 1 is 3, and 9a plus 1 is 13. 3 and 13 have a GCD of 1. But I can see that as I scroll down, things seem to be true, right? Even for 18 down here, 37 and 166 have a GCD of 1. What if I, bump up the number quite a bit? How about 500? Again, it seems like the GCD of these two integers, at least by Excel's computation, is always 1. So some pretty strong evidence that the statement is indeed true. Let's see if we can prove it now. There's our statement. Let's go back to our our board and see what we can do here. So what do we want to show? We want to show so our hypothesis is that for any integer a, the GCD of 2a plus 1 and 9a plus 4 is always equal to 1. So a proof of that statement would be such. Well, we search for an x and y and z such that what? Well, that 2a plus 1 times x plus 9a plus 4 times y is equal to 1. And this is how we're going to employ the proof that we constructed, not Euclid's lemma, the one before. If we can find a linear combination of two numbers that always results in 1, then we know that the GCD of the two numbers is 1, right? So off we go to the races, and it doesn't take much effort to see which x's and y. If we choose, let's see, x equal to, what we're going to try to do is cancel out the a's and hope that the numeric part will somehow result in 1. So let's see, if I multiply 2a by 9 and 9a by negative 2, we have what? Let's see, so it's 2a plus 1 times 9 plus 9a plus 4 times negative 2. Is that equal to 1? Let's find out. So it's 18a plus 9 plus a negative 18a plus a negative 8, which 18a and 18a negative cancel. 9 minus 8, we get 1. So since 2a plus 1 times x plus 9a plus 4 times y is equal to 1 for x equal to 9 and y equal to negative 2, we conclude that the GCD of 2a plus 1 and 9a plus 4 will always have to be equal to 1, which is a pretty astounding statement. Okay, well, that's it for now. I hope that this is giving you some insight into the rest of the chapter. I wish you luck on your homework, and I'll see you all on Monday.